Hello, so in this video we're starting on mechanics, the first part of mechanics, the first chapter, and we're going to look at modelling, right, the idea of modelling, okay. So before we start, because it's the first part of mechanics, what exactly is mechanics? Well, it's nothing to do with fixing cars or anything like that. In maths, mechanics is generally these three sort of subtopics, right, that will all group together as one. So the first part of mechanics is to do with forces. Also, mechanics is about motion and about energy, okay. These three things make up what we call mechanics, okay. It's quite physicsy, but you don't need physics for this. We do it from scratch and you don't need A-level physics or anything like that. So firstly, forces, so that's obviously like stuff that is in newtons, right? So you got, for example, weight, which kind of involves gravity, right? So the idea of weight is that it pulls you down, right? That's a force. You've got, for example, friction, stuff that slows you down. You've got air resistance. So if you like drive or something like that, the air resistance, the wind or whatever will try and slow you down, kind of like friction. And you've also got tension as well. When we deal with strings, when you pull a string, the string will exert a tension force back. Okay. Then we've got motion. So motion is to do with movement. So that is your distance, that is your speed, that's your acceleration. And also we're going to look at fancier versions of distance and speed. We're going to look at displacement and velocity. So all of this is to deal with motion, right? And energy. Now energy we won't be looking at in this in normal maths. In further maths you will consider energy as well. So that's like kinetic energy and gravitational potential, right? Which hopefully you would have met at GCSE physics, but this we won't be considering in normal maths mechanics. These two we will be, okay, quite a lot, quite extensively. We will be looking at these examples here. Okay, so that's mechanics. These, well, for normal maths, only forces and motion, stuff to do with movement and forces. Okay, right. So modelling then. So if you've done a bit of pure maths already, you would have seen the idea of modelling. Essentially, we can kind of boil down a real life scenario into sort of some mathematical equation we can solve to get some information. So the idea is this, right, of a mathematical model. We have a problem, or we want to solve a problem, right, a real life problem. And the issue is, obviously, we can't solve it exactly the way it is, so we need to make we need to simplify the problem down so we can sort of solve it. These are called assumptions. We make assumptions. Okay? Then when we make assumptions, then we can solve it mathematically. But the idea is with assumptions, because we kind of simplify the problem down, the problem isn't exactly the same as how it was. So for example, very commonly, for example, air resistance, we might want to find some forces or how fast a car moves. Commonly we will just ignore air resistance, but in reality there will be air resistance. The assumption is if we get rid of air resistance, we can then sort of do some maths to it, right? Because air resistance makes things a lot more complicated. So when we make assumptions, it won't be the same. It won't be obviously the problem will be a bit different, a bit more simplified. So that will mean we won't get an exact solution to the actual problem, but we'll get a good enough solution, right? We get a good solution, a good approximation to the solution. And that's really it, right? So the idea is we simplify problems down to get a good enough solution which kind of solves the problem, right? So that's the whole idea, okay? But obviously sometimes assumptions, sometimes there might be a bit, you kind of have to use a bit of like common sense. Like, are some assumptions realistic? Are some assumptions just too much? Stuff like that. And so, will it affect how good your solution, your approximate solution will be to solve the problem you want? Okay. So that's the idea. So what we could do then is now look at some examples of modelling in action. So we are told the motion of a basketball as it leaves the player's hand and passes through the net can be modelled using the equation h is 2 add 1.1x minus 0.1x squared. So h is the height of the basketball above the ground, and x is the horizontal distance. So because it's a quadratic expression, it's kind of going to look like this, right? So you imagine if we have a basketball, right? A basketball is going to have this sort of its movement as it moves, as it is thrown in the air. So if you imagine someone has thrown it in the air like this, that's kind of the motion of the basketball. This quadratic curve is the motion of the basketball, and eventually it will hit some sort of hoop, right? Like that. It will reach some hoop. That's the idea, right? So with that in mind, hopefully you can visualize that's what the equation's doing here. So h is the height, right? How high up it is, and x is going to be the horizontal distance. So that's the horizontal, right? That's what we're saying now. What it wants us to find firstly is the height. So remember, height is h. When the basketball is released, okay? Now, when it's released, think about it. The moment when it leaves the player's hand, the ball hasn't travelled or moved anywhere, really. So it has travelled no horizontal distance. That means then that x is equal to what? 0, sorry then, right? When the ball is released, at the instant when it relieves the back player's hand, it hasn't moved anywhere, right? So there's no distance travelled x. So we set x to 0. So the height is going to be 2 add 1.1 lots of 0 at minus 0.1 lots of 0 squared. That just leaves me 2. So that is 2. So the height is 2 meters. Now you might be thinking, wow, why is height not 0 if it's sort of like initially when it's released? Why is the height not 0? Because the ball, if it leaves the player's hand, well, the player itself has a height, right? If you imagine this as the ground level, that's saying that this height of 2, the initial height 2, is basically kind of how the height of the player in a way, right? In order for the ball to leave the player's hand, right? So it's initially, it's still at it's still like above the player, so that it has some initial height of 2 there, right? Okay, part 2. Now it wants the height at a horizontal distance of 0.5. So that is now when x is set to 0.5. So then h is going to be 2 add 1.1 lots of 0.5 minus 0.1 of 0.5 squared. At that point we just put in the calculator. And we get 2.525 meters. Okay, so when it's travelled, say 0.5 meters across it, the height from ground level, then, right, the height from ground level is 2.525. okay, so that's the idea there. Cool. Now for part B, it says use the model. In other words, use the equation, right? Use this equation to predict the height of the basketball when it's at a horizontal distance of 15 meters from the player. Okay, so now we just set x to 15. And so if we do that, then h is going to be 2 add 1.1 lots of 15 minus 0.1 of 15 squared. And then if we do that, we get -4. Interesting. -4. So then it says in part C, comment on the validity of the prediction. Well, the interesting thing here is it's a negative. It's saying the height is -4 meters. So when it's travelled 15 meters, so when it's travelled, say, 15 meters across, right? The ball, say this is 0 meters on ground level, the ball is through the ground, right? Because it's -4. So it's 4 below, right, in a way. So that is kind of nonsensical. So the validity is the model cannot work. The model is not valid, right, when x is equal to 15 meters, right? When the horizontal distance is 15 meters, right? And so yeah, so that's the reason why, because we essentially get a negative height, which kind of makes no sense here. Okay, so again, this old idea about what was discussed about some of the modelling, right? If you model a bit silly, you probably get a silly answer. So then you have to think, well, how valid is my model? You know what I mean? So that's not what we got in part B wasn't a sort of accurate answer to the problem. Okay. But yeah, but part A was, right. We got fairly sensible answers for part A. So that means that the model, the equation, can only probably work for certain values of A, for X, sorry. So that's the idea, our whole idea about modelling. You have to kind of think about, when can I use the model, when can I use an equation and stuff like that. Okay, but yeah. Okay, we've got one more question here, and we're told the motion of a basketball as it leaves the player's hand and passes through the net is modelled using the equation H is 2 add 1.1x minus 0.1x squared. It's the same one, okay, it's the same problem, the same equation. And so then it says part A now to find two values of x for which the basketball is exactly 4 meters above the ground. So again, if I my basketball is going to have that sort of motion, and then it's going to pass through some sort of hoop, right? And so then the two values from the basketball is exactly 4 meters above the ground. So then the height, right, is the height above the ground. If we want the height to be 4, then we just simply set h to 4. So if we do that, then 4 equals 2 add 1.1x minus 0.1x squared. This is a quadratic equation now, right? If I then take away 4 to both sides, I get minus 0.1x squared add 1.1x, take away 2 equals 0, right? Now, I don't really need, I could simplify the quadratic, but what I'm just going to do here is just put it in the quadratic formula to solve it quite quickly. So then x is going to be 1 minus 1.1, take a plus or minus the root of 1.1 squared, take away 4 lots of minus 0.1 minus 2 over 2 lots of minus 0.1. So if I do that, bearing in mind your calculator should have a quadratic solver function, so you can just at this point just put it right into the solver function to quickly get your answer. If you do that, you should get the two solutions. X is 8.7 meters to 1 decimal place, or X is 2.3 meters to 1 decimal place. Those are my two solutions, right? And so yeah, so those are the two values of x when the basketball is 4 meters above the ground. So let's say if we had 4 meters here, say at this point, obviously we had a ground level. Say if it's 4 meters, that's the height, right? 4 meters at this point in the path, right? That would be when x is 2.3, and here the second time when x is 8.7. Okay, hopefully it made sense. That's just the idea of what's going on here. Right, okay, then it says for part, and then it says the model is valid for 0 less than equal to x less than equal to some number k, where k is the horizontal distance from the net of the player. So k, if I get rid of this, so k is the distance from the net. So it's going to be, so from the player, so again, imagine we have a player here, the horizontal distance k here is the distance from the player to the hoop. Now, it says find the value of k. Oh no, it says given that the height of the net is 3 meters, find the value of k. So now, if the height of the net is 3 meters, right? That's saying from the ground to the hoop it's 3 meters. So h is 3, very simply. So if h is 3, then we plug that into the equation. So then h is 3 equals 2 add 1.1x minus 0.1x squared. And again, we solved this quadratic. So minus 0.1x squared add 1.1x. If we take away 3, we get minus 1 equal to 0. Okay, then x is going to be minus 1.1 plus or minus the root of 1.1 squared, take away 4 lots of minus 0.1 minus 1 over 2 lots of minus 0.1 to get x is 10 or x is 1 meter. Okay, in meters. Those are my two solutions for x. Again, remember x is the horizontal distance, so that length there horizontally from the ball at the start to the net. Okay, so we've got two values, but hang on, it said find the value of k, so k can only be one of these values of x then. Which one? Well, this is where again you have to kind of consider exactly what's going on here with the motion. So if I look at this diagram again, if I get rid of it, if I look at this diagram here again, so at 3 meters, right, again 3 meters from the ground to the hoop, that'll be this point on the curve, right? This is when the height is 3. You can see that this height crosses the curve 2 times, right? This quadratic curve, which is this equation here. We can see there's 2 points. That's going to be 10 and 1. Okay? So at that point, hopefully you can spot then, it makes more sense for the k being the length, right? The distance to the hoop is going to be 10 then, right? When x is 10. Okay? And that makes sense as well, because if we said x is 1, what essentially happened was, we have a hoop here, let's say we have 1 here, and then we have, the ball here, sorry, the basketball, then at 1, that would be where the hoop, if the hoop was there at when x is 1, that's basically saying it just passes through the hoop upwards. You kind of have to think about, can a ball just go up through the hoop? Not really. The ball has to come down to the hoop, not up through the hoop, if that makes any sense. So anyway, so from that, k has to be 10 then, okay? K has to be the larger of the two values. So k equals 10 meters, okay? Hopefully that made a bit of sense. It's quite hard, especially at first, to get that sort of intuition about the motion and sort of being that physics frame of mind for why we have to take the second solution here when it's 3 meters upwards, okay? Right, and then it says, explain why the model is not valid for x greater than k. Well, again, as you can see here, when x is equal to 10, so again, what the 10 saying is, initially when the basketball is flung from the person, and then to the hoop that's 10 meters across. If we were to go any more than 10 meters, right, the ball will just come down, and then we don't really care about anything after that. We only care about when it just hits the net, right? We don't care about any subsequent or future motion after that, okay? So for that reason, really, the model's not valid, because we don't intend to use it really for once it passes through the hoop, okay? So I'm going to say at x equals 10, the ball passes through hoop. So the model is not useful after it passes through the hoop. And that kind of makes sense as well, because if the model was to go on and on and on and on, right? If we just continued the curve on, it would then pass through the floor again. There'd be points where once this quadratic curve passes through the ground floor, it particularly goes under the floor, because if we got a quadratic curve, it would then become negative. So that's kind of the idea, right? And also, I just thought I'd show this. If my drawing was a bit horrible, from the solutions, there's a nice visual for what's going on here.